Chapter 4, Matrix Multiplication. In this chapter, we're going to learn how to partition matrices into rows and columns, how to multiply one matrix by another, and how to swap rows of matrices. The outcomes are multiplying a row vector by a column vector, recognizing the rows and columns of a matrix, standard definition of matrix multiplication, size restrictions when multiplying matrices, examples that work and those that don't, and permutation matrices. Here is a row vector A and a column vector B. Both have k elements. To compute their product, we multiply their corresponding elements and sum over all of them. Another way to write this, we can write a row vector dot a column vector and expand the summation on the right hand side. Here's an example. A is a 1 by 4 row vector and B is a 4 by 1 column vector. Because they have the same number of elements, the product is defined and we can compute it using either notation that you prefer. We can also try this in Julia to confirm our hand calculation result. Notice that A is defined as a row vector and B is defined as a column vector. Now we're going to look into how to partition matrices into row and column vectors. Here A is a 2 by 3 matrix. We can partition A into 2 row vectors. Each row vector has the same number of columns as the original matrix. We can also partition A into 3 column vectors. Each column is a 2 by 1 vector and has the same number of rows as the original matrix. In general, for an n by m matrix, we can partition the matrix into n rows or m columns. Now we're going to look into the standard matrix multiplication. If we have a matrix A, this is n by k, and we have another matrix, which is k by m matrix, we define the standard multiplication to be an n by m matrix. So the product is defined by multiplying rows of A by columns of B and summing over the common index. So that's why the number of columns in A must be the same as the number of rows in B. And by summing over the common index, the result is an n by m matrix. The values of n, m, and k must be any integers greater than 1 or equal to 1. So the standard way of multiplying matrices involves multiplying rows of A by columns of B. However, in general, A times B is not equal to B times A, even if A and B are square matrices. In the language of math, we say that matrix multiplication is non-commutative. Now let's look into some examples. Here A is a 2 by 2 matrix. We partition A into 2 row vectors. B is just a column vector, and we can partition it into 1 column vector. A times B is defined. We can multiply each row of A by B, and here we see the detail of calculation. We can confirm this in Julia by defining A and B and simply typing A times B. Another example, If we reuse A and B, can we multiply B by A? And the answer is no, because B is a 2 by 1 vector and A is a 2 by 2 matrix. The number of columns of B does not match the number of rows of A. You can try this in Julia and you will face a syntax error. And the error says dimension mismatch. In this example, both A and B are square matrices. Therefore, we can define A times B as well as B times A. But we can see that the results are different. As expected, we know that matrix multiplication is non-commutative and the order of multiplication matters. We can confirm this in Julia and we will see that A times B is not the same as B times A. In general, if A is an n by k matrix, we can partition A into n rows. And if B is a k by m matrix, we can partition B into m columns. And the product is defined, as you can see, for each entry of the result. We have the corresponding row of A times the corresponding column of B. Another way to see this pattern is by partitioning A into its rows and partitioning B into its columns. And in the result, we see that each entry of the matrix product is the summation over the common index over rows of A and columns of B. Next time, we're going to see permutation matrices.